In the various branches of mathematics that fall under the heading of abstract algebra, the kernel of a homomorphism measures the degree to which the homomorphism fails to be injective. An important special case is the kernel of a linear map. The kernel of a matrix, also called the null space, is the kernel of the linear map defined by the matrix. The definition of kernel takes various forms in various contexts, but in all of them, the kernel of a homomorphism is trivial if and only if the homomorphism is injective. The fundamental theorem on homomorphisms is a theorem, again taking various forms, that applies to the quotient algebra defined by the kernel. In this article, we first survey kernels for some important types of algebraic structures, then we give general definitions from universal algebra for generic algebraic structures. Survey of examples. Linear maps. Let V and W be vector spaces and let T be a linear map from V to W. If 0W is the zero vector of W, then the kernel of T is the preimage of the zero subspace 0W, that is, the subset of V consisting of all those elements of V that are mapped by T to the element 0W. The kernel is usually denoted as ker-T, or some variation thereof. Since a linear map preserves zero vectors, the zero vector 0 via V must belong to the kernel. The transformation T is injective if and only if its kernel is reduced to the zero subspace. The kernel ker-T is always a linear subspace V. Thus, it makes sense to speak of the quotient space V. The first isomorphism theorem for vector spaces states that this quotient space is naturally isomorphic to the image of T. As a consequence, the dimension of E equals the dimension of the kernel plus the dimension of the image. If V and W are finite dimensional and bases have been chosen, then T can be described by a matrix M, and the kernel can be computed by solving the homogeneous system of linear equations MV equals 0. In this case, the kernel of T may be identified to the kernel of the matrix M, also called null space, of M. The dimension of the null space, called the nullity of M, is given by the number of columns of M minus the rank of M. As a consequence of the rank nullity theorem, solving homogeneous differential equations often amounts to computing the kernel of certain differential operators. For instance, in order to find all twice differentiable functions f from the real line to itself such that xf plus 3f equals f, let V be the space of all twice differentiable functions, let W be the space of all functions, and define a linear operator T from V to W by equals xf plus 3f minus f for f in V and x and arbitrary real number. Then all solutions to the differential equation are in ker-T. One can define kernels for homomorphisms between modules over a ring in an analogous manner. This includes kernels for homomorphisms between abelian groups as a special case. This example captures the essence of kernels in general abelian categories. See kernel. Group homomorphisms. Let G and H be groups and let F be a group homomorphism from G to H. If A is the identity element of H, then the kernel of F is the preimage of the singleton set A, that is, the subset of G consisting of all those elements of G that are mapped by F to the element A. The kernel is usually denoted ker-F in symbols. Since a group homomorphism preserves identity elements, the identity element e.g. of G must belong to the kernel. The homomorphism F is injective if and only if its kernel is only the singleton set, e.g. It turns out that ker-F is not only a subgroup of G but in fact a normal subgroup. Thus, it makes sense to speak of the quotient group G. The first isomorphism theorem for groups states that this quotient group is naturally isomorphic to the image of F. In the special case of abelian groups, this works in exactly the same way as in the previous section. Ring homomorphisms. Let R and S be rings and let F be a ring homomorphism from R to S. If 0S is the zero element of S, then the kernel of F is its kernel as linear map over the integers, or, equivalently, as additive groups. It is the pre-image of the zero ideal, 0s, which is the subset of R consisting of all those elements of R that are mapped by F to the element 0s. The kernel is usually denoted kerf in symbols. Since a ring homomorphism preserves zero elements, the zero element 0R of R must belong to the kernel. The homomorphism F is injective if and only if its kernel is only the singleton set 0R. It turns out that, although kerf is generally not a subring of R since it may not contain the multiplicative identity if S is not the null ring, nevertheless, it is a two-sided ideal of R. Thus, it makes sense to speak of the quotient ring R. The first isomorphism theorem for rings states that this quotient ring is naturally isomorphic to the image of F. To some extent, this can be thought of as a special case of the situation for modules, since these are all bimodules over a ring R. R itself, any two-sided ideal of R, any quotient ring of R, and the codomain of any ring homomorphism whose domain is R. However, the isomorphism theorem gives a stronger result, because ring isomorphisms preserve multiplication while module isomorphisms in general do not. This example captures the essence of kernels in general Malchev algebras. Monoid homomorphisms, let M and N be monoids and let F be a monoid homomorphism from M to N. Then the kernel of F is the subset of the direct product M times M consisting of all those ordered pairs of elements of M whose components are both mapped by F to the same element in N. The kernel is usually denoted kerf in symbols. Since F is a function, the elements of the form must belong to the kernel. The homomorphism F is injective if and only if its kernel is only the diagonal set M in M. It turns out that kerf is an equivalence relation on M, and in fact a congruence relation. Thus, it makes sense to speak of the quotient monoid M. The first isomorphism theorem for monoids states that this quotient monoid is naturally isomorphic to the image of F. This is very different in flavor from the above examples. In particular, the pre-image of the identity element of N is not enough to determine the kernel of F. This is because monoids are not Malchev algebras. Universal algebra. All the above cases may be unified and generalized in universal algebra. General case: let A and B be algebraic structures of a given type and let F be a homomorphism of that type from A to B. Then the kernel of F is the subset of the direct product A times A consisting of all those ordered pairs of elements of A whose components are both mapped by F to the same element in B. The kernel is usually denoted kerf in symbols. Since F is a function, the elements of the form must belong to the kernel. The homomorphism F is injective if and only if its kernel is exactly the diagonal set A. It is easy to see that kerf is an equivalence relation on A, and in fact a congruence relation. Thus, it makes sense to speak of the quotient algebra A. The first isomorphism theorem in general universal algebra states that this quotient algebra is naturally isomorphic to the image of F. Note that the definition of kernel here doesn't depend on the algebraic structure, it is a purely set-theoretic concept. For more on this general concept, outside of abstract algebra, see kernel of a function. Malchev algebras. In the case of Malchev algebras, this construction can be simplified. Every Malchev algebra has a special neutral element. The characteristic feature of a Malchev algebra is that we can recover the entire equivalence relation kerf from the equivalence class of the neutral element. To be specific, let A and B be Malchev algebraic structures of a given type and let F be a homomorphism of that type from A to B. If F is the neutral element of B, then the kernel of F is the pre-image of the singleton set EB, that is, the subset of A consisting of all those elements of A that are mapped by F to the element EB. The kernel is usually denoted kerf in symbols. Since a Malchev algebra homomorphism preserves neutral elements, the identity element each of A must belong to the kernel. The homomorphism F is injective if and only if its kernel is only the singleton set each. The notion of ideal generalizes to any Malchev algebra. It turns out that Ker F is not subalgebra of A, but it is an ideal. Then it makes sense to speak of the quotient algebra G. The first isomorphism theorem for Malchev algebra states that this quotient algebra is naturally isomorphic to the image of F. The connection between this and the congruence relation is for more general types of algebras is as follows. First, the kernel as an ideal is the equivalence class of the neutral element each under the kernel as a congruence. For the converse direction, we need the notion of quotient in the Malchev algebra. Using this, elements A and B of A are equivalent under the kernel as a congruence if and only if the quotient A, B is an element of the kernel as an ideal. Algebras with non-algebraic structure. Sometimes algebras are equipped with a non-algebraic structure in addition to their algebraic operations. For example, one may consider topological groups or topological vector spaces, which are equipped with a topology. In this case, we would expect the homomorphism F to preserve this additional structure. In the topological examples, we would want F to be a continuous map. The process may run into a snag with the quotient algebras, which may not be well behaved. In the topological examples, we can avoid problems by requiring that topological algebraic structures be Hausdorff, then the kernel will be a closed set and the quotient space will work fine. Kernels in category theory. The notion of kernel in category theory is a generalization of the kernels of abelian algebras. See kernel. The categorical generalization of the kernel as a congruence relation is the kernel pair.